Okay, so we are in Statistical Rethinking, Chapter 9, second edition of Statistical Rethinking, I should say. Okay. So we're in the hard problems, and we're on question 9H6. And in the previous question, we took the hand-coded Metropolis algorithm in the context of the island hopping example that's given earlier in the chapter. Okay, so you may want to go look at that video or reread that section. But anyway, we kind of made the Metropolis algorithm to kind of fit that situation. Okay. Now we are going to write the Metropolis algorithm, but for a different context, and so we're going to go all the way back to chapter 2 in the globe tossing example. Okay, and so I'll kind of go over that here in a second. But again, we're going to write the Metropolis algorithm for all of that. Okay. The globe tossing model, if you recall, was the idea that you had some people and they had a globe and they were tossing it, and whenever somebody caught it, they looked at where I think their index finger was, and recorded if it was on land or as water. And the idea was that we were going to repeat this many, many times as a way of estimating the proportion of water on the globe. Okay, so that model then would look like this, where water was the proportion of the globe covered in water, and it was a binomial distribution with n data points and the parameter p, where p is the proportion of water on the globe. And the prior for p was a uniform distribution between 0 and 1. Okay. Now, in that experiment, we gathered some data. So we had n equals 9, where we found 6 waters and 3 lands. Okay. And so now we're going to try to adapt the Metropolis algorithm that, well, let's be honest, we didn't write it. It was in the book, and we kind of tweaked the code a little bit. So we're going to tweak the code a little bit to fit this particular example. Okay, so I'm going to so we're going to do that, and I'm just going to give you a heads up now that I am going to, even though the question doesn't ask us to, so in the initial or in the previous question we ran one chain, right, and that one chain maybe looked like this here, but I'm going to run 2 chains because I also want to estimate how well our model mixed. Okay. So anyway, so everywhere where you see something like this, it's going to have a 1 or a 2. Okay, and that's going to refer to our 2 chains. All right. So so here's the code. Again, you can go to the Colab sheet, assuming that my saving doesn't fail, like it says it's going to down here. But let's just kind of walk through this in a little bit of detail. So we're going to run this chain for 10,000 iterations, and the output of each iteration is going to be a sample for p. Okay, and so I'm creating these 2 vectors here that are going to collect our different outputs of p. Okay, so I just have these 2 vectors here that have length 10,000. Okay, which is the number of iterations we're going to run. Okay. I'm going to, so the first thing that I do is I need to initialize the values for these 2 things with P1 and P2. And so I'm just going to randomly generate a value between 0 and 1 for both of these as the initial value. You can assign a hard value, you can, maybe you want to assign 50% or whatever, but I'm just going to kind of let it go all over. Okay. And then there is this little guy right here, the proposal width. Okay, now when I highlight it, you can see where it's coming into play. And so I'll talk about that when we get there. But this is something that we can adjust. And in fact, at the end of all of this, you may want to go back and adjust this, okay? And look at the consequences. Okay. And then we also have our data. We had 9 tosses, and we found 6 waters. Okay. So we're going to go through this loop. Again, we're going to run this loop here 10,000 times, or n, capital N times. Okay. So I start out by assigning p, the value of p1, which I've hard-coded, and then I'm going to make a proposal. And that proposal is going to be anchored to the current value. Okay. So what is that proposal going to be? Well, it's going to be anchored here, and then I'm going to go above or below it. How much am I going to go above or below it? Well, I'm going to go half of this proposal width. Okay. So the larger that you set proposal width, the larger your steps will tend to be. And the smaller you set it, the smaller your proposal steps will tend to be. Okay. So if I have a proposal width of 0.1, then that means that I will go so I'm dividing that by 2, I'll go 0.05 percentage points below and 0.05 percentage points above. Right? That's going to be my window of possible proposals, and I'm going to randomly sample from that window. Okay. So remember, in the island hopping example, we either sampled, if we were on island 7, we either sampled 8 or 6, and those were and those islands were discrete entities. But the values that our parameter here can take on are not discrete. We can go all over the place. So that's why we have to make this adjustment. Okay. And now, if we just followed that rule, well, we could be at, we could have a current value for P or P1 that's very close to 0, and then we could, go well below 0. So we have to make sure that we're not proposing negative values of P, and we also can't propose values of P greater than 1. Okay, so we have to set up these rules here, right? So if we go below 0, then we just take the absolute value of it, right? So if we're at 0.1 and we propose, or if we're at 0.01, 1%, and we propose negative 4% from that, right? Then we'll just go to 4%, okay? And similarly, if we make a proposal that's above 1, then we need to somehow come back under 1. Okay, and that's the rule here. So you can look at the arithmetic for that. Okay. Now, in the initial island hopping example, when we were trying to determine if we were going to move, we could just use this bit of the code right here. Okay, and the reason is because our islands 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 were connected to the proportion of their populations, right? So the fact that the label of the island was synonymous, more or less, with the proportion at which it would be visited, basically was acting as the posterior probability. But here we actually have to calculate the posterior probability for the current and proposed values of P. Okay, and so to do that, first we need a likelihood. Okay, so we have the likelihood of the data. Okay, right. So we had 6 waters and out of 9 tosses. Okay, and so P1 is going to, with P1 we will find that data, P% of the time, or P1% of the time. And then with the proposed P, we will find that data distribution, proposal 1% of the time. But of course, that's not the complete story, because we also need to normalize this. Well, I shouldn't say normalize it. We need to take account of the prior distribution. Okay, right? So if we're going to have a posterior, we need to multiply the likelihood by the prior. Okay, and so here we are just assuming a uniform distribution between 0 and 1. So this is just a flat prior. Okay, so in effect, it's not really doing much here, but you could play with this, right? You could make this a normal distribution. You start to run into a little bit of some problems, though, because normal distribution can propose above and below 0 and 1, or 1 and 0, and so you would need to make some adjustments to your code. So just to keep the code as simple as possible, we're just using distribution that definitely can't go below 0 and definitely can't go above 1 for the prior distribution. Okay. So again, we have that for 1 chain and 2 chains. Now we can calculate the probability of moving for either chain, which again is just the proposal divided by the current. Okay. and then we compare that to a randomly generated number, again between 0 and 1. And so if the proposal, or so, well, if P move, right, is greater than that number, then we move, otherwise we stay. All right. So we can run this, and it runs pretty quickly. So that's all 10,000 iterations over 2 chains have just ran. Okay, very quick. So now let's check the mixing of our chains. All right. So I'm going to do this with a trace plot. So and remember we have 2 chains, so I have 2 bits of code here. Okay. And that looks, not bad. So that's interesting. Let me just quickly, let's also calculate the R hat value, and then we'll go back and play with some things. So the R hat is basically, it's not quite this, but it's a comparison between the within chain variance, so the variance within the chains as though they were just one big long chain, and then the variance between the chains, right? So I take the mean of one and the mean of the other, and I find the variance in the means of the chains, okay? And so the idea is that if we have good mixing, then all of the variance, or close to all of the variance, should be coming from the within chain variance, okay? And so that's all of this, okay? And so so the total variance then is given by the within and the between, okay? So I'm adding the within chain variance to the between chain variance, weighted by the number of samples. But and then the R hat value is just the square root of the total variance divided by the within chain variance. And again, if the within chain variance is accounting for all of the variance, or close to it, then these 2 values should be equal. In other words, this value right here should be, should approximate 0. And so, anyway, so when we run that, we get a value of 1, okay, which indicates pretty good mixing. Okay. So let's go back and adjust this proposal width thing. Okay. So first, we're at 0.1 right now. So let's make it 0.01. So we'll go down an order of magnitude here. We'll run that, and it should go pretty quick. But now notice that this makes our proposal widths much smaller, right? And so let's see what happens to these chains here. Not very good, okay? And so that should be reflected in the R hat value here. Okay, I'm not really sure. Well, I guess that kind of makes sense. But I don't think that we would call this very good mixing, okay? Interestingly, the R hat value is pretty good, right? Which shows you why we need to check. We have to run multiple diagnostics on all of this, okay? But can you kind of imagine what's happening here? So we can only make itty bitty adjustments, and so as we're going along here, the inflection up or down from any given point is very, very small. Okay, so what will happen then if instead of making this 0.01 or 0.1, we make this, I don't know, let's make it 0.8. Okay, so I run that. I'm not really sure what's going to happen here. I might say that's better. So anyway, but you can go through and play with this over and over and over again, and just kind of look at the consequences. Well, anyway. So yeah, so really 0.1 does not seem that great to me, but anyway. All right. So but now that we're satisfied with the mixing, let's go ahead and look at what our estimates are for the posterior of P. Right. So I'm just going to plot it as a histogram and then look at the mean as well as the standard deviation. Although I should say that the variance of a well, it doesn't matter. Okay. So so if I run this, so we get a posterior distribution where the mean is about 0.62. So in other words, the estimate for the probability of water given the confines of our model is about 62%. Okay, not bad. All right, I guess we will call that good.